presentation on Lab 9, Equilibrium of a Solid Due to 3 Forces. I'm Hannah, and this is
Luke. And I'm Michael.
Adalmys.
In this lab, we'll explore the fascinating world of static equilibrium in solid bodies subjected to multiple forces. The main objective of today's lab is to experimentally verify that the net torque is zero for a solid in static equilibrium and to use both a force table and a rotational inertia apparatus to analyze this condition.
In the theory section, we have the formulas. We have first torque, which is the capacity of a force to produce rotational motion, which happens when the center of a mass is moving in a circle. We have R, representing lever arm and length meters with units. We have F, force of magnitudes in units of newtons. We have T for torque in units of newtons times meter. Then we have the lever arm. R is the perpendicular distance from the pivot to the line of action. We also have here the net of force, which is equal to 0, and whenever this is equal to 0, then the net of torque is also equal to 0. And then we have force equals mass times gravity.
To conduct this experiment, we use a blank white sheet of paper with a 1-inch hole in the center, a ruler, 3 pulleys, a ring with 3 strings attached, a force table, and a few different weights. The purpose of today's activity is to practically apply the principles of static equilibrium. By positioning weights and measuring their effects on a simulated system, each of us determined the conditions under which the net torque around our chosen rotational axis is 0, thus proving that the net torque at any given rotational axis of a solid at static equilibrium is 0.
In order to do this lab, the first thing that you're going to probably want to do is find the exact center point of your piece of paper. To do this, you're just going to take a ruler and then measure the length and the width of the paper and then draw lines that go across the length and the width using those measurements. Next, you're going to want to make a 1-inch circle in the middle of your piece of paper. And in order to do this, you're going to use the ruler again in order to mark out 1-inch boundaries for your circle. To actually draw the circle, you can use a protractor, but for me, I'm really bad at using protractors. So instead of actually using it, I ended up just freehanding the circle. Now that you have your 1-inch circle, what you're going to want to do is then cut it out. Once you have it cut out, what you're going to want to do is put it onto your force table. In order to make it fit with the pulleys, what I recommend is actually just folding the piece of paper so it fits perfectly onto your force table. The next step is going to be to take 3 strings and pull it through that center hole. Once you do that, you're going to want to set up your pulleys at first 330 degrees, then 180 degrees, and then at 30 degrees. And as you can see, we're tightening the pulleys here. Next, what you're going to do is add weights to make sure that in the center, those circles line up perfectly. What you can do next is then trace the strings so that you can draw your lines of action. As soon as you're finished drawing your lines of action, what you're going to want to do is then realize that you set up the lab the entirely wrong way, and then go back and set it up the correct way using this ring with 3 strings. Make sure that the pulleys are high enough to make sure that the object is above the piece of paper. Again, add weights to make sure that the ring in the center lines up with the hole in the force table. Once you have the ring that lines up with the hole, what you're going to want to do is finish your lines of action and add next to them the angle measure and the amount of weight that you put on the string. Finally, after making 4 copies of the same piece of paper, what you're going to want to do is have each of your lab partners choose a random point on the piece of paper, one that is not actually on the lines of action, and then draw a line to that point on your piece of paper. Now that we have the angle and weights associated with our lines of action and our chosen axis of rotation, we first want to draw perpendicular lines from our axis of rotation to each line of action. For this third line of action, we will have to extend it through the origin in order to draw our final perpendicular line. Next, we want to find the force associated with each line of action. In order to do this, we use the equation force equals the mass we put on each string in kilograms times acceleration, which in this case is just acceleration due to gravity. Our next step is to then measure the length of each of our perpendicular lines and record their lengths in meters. The conversion to meters will be important for the next step. Now equipped with the force associated with each line of action and the length of each of our perpendicular lines, we are now able to calculate the torque. The way we do this is by taking the length of a perpendicular line and multiplying it by the force of the line of action that the perpendicular line intersects. We will do this for each perpendicular line. We then want to determine how each perpendicular line rotates around our axis of rotation. Following the pull of each line of action, we are able to determine in which direction each line rotates. Counterclockwise and clockwise can both either be positive or negative, but for our case we decided that clockwise will be positive and counterclockwise will be negative. Assigning positive and negative signs to each perpendicular line based on their direction of rotation, we can now finally calculate the net torque, and using that net torque we can calculate absolute error. The reason why we don't calculate percent error is because the expected net torque at any chosen axis of rotation should be 0, and of course, you cannot divide by 0. Thus, the method for this lab is simply using algebra and known values to calculate the net torque.
So our results are as follows, but before we get to that, we're going to say that clockwise is going to be our positive values and counterclockwise are going to be our negative values. And so for my first lever arm, the torque around that one was 0.0620 Newton meters. And then lever arm 2 was 0.0851 Newton meters. And then lever arm 3 was negative 0.147 Newton meters. After we sum all these up, we get a net torque of 0.0001 Newton meters with an absolute error of the same exact amount.
The torque of lever arm 1 was negative 0.0948 newtons times meter. The torque for lever arm 2 was negative 0.0423 newtons times meters. And lastly, the torque for lever arm 3 was 0.1401 newtons times meters. And the net torque was 0.003 newtons times meters with an absolute error of 0.003 newtons times meters.
From our results, I got lever arm 1 at 0.182 Newton meters, and this was clockwise according to our legend up there. For lever arm 2, I got negative 0.129 Newton meters, which indicates counterclockwise direction, and lever arm 3 was a value of negative 0.0520 Newton meters, and that also indicates counterclockwise direction. So taking the sum of all of these values, we found a torque net of 0.001 Newton meters, which gives an absolute value of 0.001 Newton meters.
In this section, lever arm is 0.0541 Newton size meters per units. Then lever arm 2, we have negative 0.178 Newton size meters. Lever arm 3 is going to be 0.123 and Newton size meters per units as well. And the net torque over here, we have 0.0009 Newton size meters and absolute error of the same value.
So, the main idea of this lab was to use a force table along with assorted weights connected by strings to a central ring in order to verify that the net torque of a solid is zero at static equilibrium around any rotational axis that we chose. Therefore, since the net torque was extremely close to zero, for example, our lowest net torque was 0.0001 Newton meters. This indicates that the rotational axis was at equilibrium, at static equilibrium specifically. Also, because our absolute error was 0.0001 Newton meters, this indicates very good accuracy. Furthermore, the lines of action. So we had two questions on the line of action. The lines of action are on the same plane. This is because when we had the pulleys set up on the force table, the pulleys were all at the same level. Therefore, the lines of action must be on the same plane. Also, the lines of action intersect at a single point. So when we drew onto the force table, they all intersected at the point called the origin, and that is the center of the ring. Torque produces the basis for human movement and biomechanics, which is the study of the forces that affect structures of the human body. Torque is especially important in certain aspects of healthcare, such as in physical training, physical therapy, exercise training, and other sport training. Torque is an important concept because it allows for movement of levers of the body, such as bones. Therefore, it is especially useful for coaches and athletes. For example, while exerting torque is important for an athlete, understanding how to limit the amount of torque produced is vital in order to reduce injury. This is shown here. This is a normal torque. Therefore, there is no injury. However, if the athlete produces excessive torque, there is now an injury to the lever specifically. Therefore, understanding how to limit this amount of torque produced is vital in order to reduce the amount of injury to biological structures such as bones and muscles if the torque is exerted excessively.